All right, so in the last class, we were discussing about the proportional LOS guidance scheme, where the idea was that if given a path that I want to follow here, and I'm very far away, I'll initially try to approach it perpendicular, but then as I come closer, I try to approach the path along its tangent so that I have a smooth way to get onto the path rather than an abrupt change in my direction. And the control law was basically based on providing a desired course angle as pi p, where that is the angle between the two waypoints, line joining the two waypoints, and minus tan inverse kp times the side track error or the cross track error. So this is like a proportional control where I'm taking the cross track error, multiplying it by some factor, so by some proportional factor, and that is being used to give me my desired course angle. That is the main idea. We also understood that generally this Kp value is chosen as 1 by delta, where delta is my look ahead distance. So I'm actually looking at a path where, or I'm looking at a point on the path connecting the two waypoints at a distance delta away from my current location, okay, or along the path basically. So that delta is not measured as the distance from the craft to the point that I'm observing, but rather along path distance is that delta. And we looked at the idea that if I look at the dynamics of the cross-track error, so if I take a derivative of the YPE, you'll observe that that is nothing but the angle U times psi PE. Okay, so which means that I'm actually looking at this angle right here, which is the course angle, which means it is the angle between the velocity vector and the x-axis of the system, which is pointed from one previous waypoint to the next waypoint. That is what it is looking at. And that can be represented, that chi p can be represented as chi minus pi p. And here we are assuming that we have a perfect autopilot, which means that our controller is able to precisely track the course angle that we want it to track with no error. Okay? That is a big assumption. And sometimes it may not hold as well. So when we are looking at the controller, we have to make sure that the convergence speed of the controller is much faster than the convergence speed of the guidance system for us to be able to make sure that this works perfectly in a practical world. Okay, so this course angle minus pi p is nothing but tan inverse of YPE by delta, which gives us this dynamics for our cross-track error. So YPE dot is given by minus U times square root of delta square plus YPE square times YPE. So notice that what is happening in this, as YPE is becoming larger and larger, what is happening to YPE dot? What is becoming YPE dot? Almost
saturated level.
Yeah, but what is it saturating to?
U.
It's actually not saturating. It's becoming a small value. Right? Because it is becoming U, YPE dot is becoming U divided by YPE of some sort. Because delta is very small compared to YPE. So you are kind of assuming that it is almost approximately equal to U by YPE. Okay. So that is where we are trying to see that this allows us to make sure that the craft is actually coming at an angle perpendicular to the path, because this sine of this angle, YPE is large, tan inverse is becoming pi by 2, and sine of pi by 2 is becoming 1, which means our craft's entire velocity is oriented directly to mitigate the YPE. Is everybody following me? Yes. I think I made a mistake here. Sorry, this is a mistake here. This will actually come down to U. It will saturate to the value of U minus U, because of the square root, right? So if YP is really large, this delta can be neglected. So then basically I have YP divided by mod of YPE. Right? So it is kind of something like minus of sine of YPE times U. So no matter what am I doing, I'm always trying to hone with my craft in such a manner that I'm trying to basically mitigate my cross-track error first rather than anything else. So all of my efforts is focused towards that idea. Again, we looked at the idea that through Lyapunov methods, we can show that if we choose the Lyapunov function candidate as this, I'm actually hearing an echo from someone. I do not know someone. Krishna Velu, I think I'm hearing from you. Yes. Okay. All right. So if I choose a candidate Lyapunov function, 1/2 of yp square, and I take a derivative of that with respect to time, we can see that this derivative will always be less than 0 for all ype not equal to 0. And that kind of proves that this is globally asymptotically stable. We also looked at the idea in the last class that in fact we can prove a much stronger stability criterion for this system. We can in fact show that the system is uniformly, semi-globally, exponentially stable. And we understood that this condition is quite important from a robustness perspective. And we also observed that we can't look at a global exponentially stability cannot be achieved because of the kinematic representation, where we are taking with respect to this trigonometric functions, so there is some saturation which occurs. So therefore, we can't actually prove that the system is globally as exponentially stable. It actually depends on the initial choice of where the trajectories are lying. The C of R actually depends on that. That's what we saw in the previous class. So that is why we have this semi-globally exponential stability. Okay, so today we're going to continue forward. We're going to take a look at time varying look ahead distance. So let us say that we want to take this delta and make it time varying. And it actually, let's say, depends on the magnitude of the cross-track error. So I want to kind of be adaptive in nature in some sort, that as my cross-track error is decreasing, how should I go about my delta? And let's say that this delta varies between some minimum value and maximum value. Okay, so if I choose something like this function, which you see here, and if I plot it versus YPE, you'll see that this function looks something like that. And maybe not exactly like that, maybe something like that. And similarly, it looks the same way the other way. So it asymptotically reaches the value of delta min, but starts at the value of delta max. It's a simple exponential function. As you see that as YPE increases, this term goes to 0. So what you're left with is delta minimum. But when YPE is 0, then you actually have the delta maximum as the value which comes out of it. Okay. It's not very hard to see this function is actually varying between delta minimum and delta maximum. Sometimes you may want to choose the mean absolute value of YPE to formulate this function. An alternative approach might be to look at YPE square. Only difference being that the decrease will be much sharper when you take YPE square. Okay, so because the value will be much bigger, so it will decay much faster. That's all is the idea. And typically, you'll see that one can choose between either of them depending on the situations. As a designer, you have the choice. But there's no necessity that you should choose exactly like this. You can choose a different form also if you're really interested in it. Okay. The idea here is that when YPE is small, we are choosing a large value of delta, which means that, so if this is my path and I'm close by, I'm really taking a large look ahead distance. Whereas if I am very far away, then I am taking it a very short look ahead distance. Okay, so which means that when I am not close to the path, I am being more aggressive to try to come towards the path. But as I am coming closer to the path, I am trying to be less aggressive and want to kind of join the path in a tangential manner. Okay. So you can choose delta to be a time varying quantity as well. A small delta usually results in a more aggressive maneuver, whereas it tends to decrease the cross-track error faster, whereas a larger delta results in a less aggressive behavior and tends to decrease the cross-track error slowly. The idea of decreasing this cross-track error slowly is that we can avoid overshooting. So which means that if I am coming from one side, I don't want to be looking at this sort of a convergence, but rather I want to be looking at a smooth convergence onto the path. Okay, so it tries to avoid overshooting as much as possible. For small YPE, the cross-track error dynamics is more or less linear. So you can see that when YPE is small, you can approximate this side of it as minus U by delta times YPE, which can be written as minus lambda times YPE, where this lambda is nothing but I'm defining this value of U divided by delta as my value lambda. Okay, so that is my design parameter, which I usually change when I want to look at how fast a convergence do I need or how slow a convergence do I need. In fact, since this is governing the dynamics for small YPE, this will actually give me a bound on delta max, right? So that I'll be able to choose delta max by specifying a particular value of lambda. It'll just be clear in just a second. Just bear with me here. So if you look at the idea as to what happens to the coarse angle as YPE tends to 0, we know that coarse angle is given by pi p minus tan inverse of this quantity. And then as YPE tends to 0, this tan inverse will tend to 0. So what I'll be left with is pi p, which means that in the eventuality, my path of the vehicle is along the 2 points connecting the waypoints. That's what I'm getting on. Notice that since we were dealing with what you call smaller YPE and we were trying to make an approximation, this choice of lambda, which is our design parameter, determines basically what is my Umax. So for a given speed of the craft, once I choose lambda, I can basically establish what is my maximum look ahead distance that I want to look at. Okay. All right. Now, in a similar manner, when I look back and see what is happening at large YPE, you'll see that as YPE tends to infinity, this coarse angle becomes pi p minus tan inverse of YPE by delta, and as YPE tends to infinity, this tan inverse value tends to pi by 2. Okay, so it's actually starting to be looking at a 90 degrees out of phase from the angle of the path joining the 2 waypoints. So I'm trying to approach the path perpendicularly as I am farther away. So the graph basically moves perpendicular to the path of the travel when it is very far away. Now delta minimum can typically be specified according to delta minimum being some fraction of delta max. So therefore a sigma value we can define as the ratio of the delta minimum to delta max as another design parameter which a control engineer can play with. So when you're actually looking at a guidance law to be formulated for your vehicle, you're basically trying to establish what should be my lambda and what should be my sigma, which will give me a smooth enough path so that I do not see large overshoots and I can track the path aggressively when I am far away and more mildly try to have less overshoots as I come closer to the actual path. Is that making sense? Yes, no? Is there a confusion? Any questions? No questions. Okay. This is just an added advantage. So instead of choosing a fixed value of look ahead distance, I can actually also play around with it in my guidance algorithm. So it's giving you a little more freedom to wiggle room to look at what is happening with the guidance path and can I change and play around with it a little bit more, keep it more aggressive. If I want to have a very sharp aggressive maneuvers, what should I do with delta? You can adjust with it. You can play around with it. That is what is the idea. All right. Now, so far we looked at the what you call look ahead based steering. And that is what this control law was, where we were looking at the course angle desired is given by the path tangential angle minus the relative angle between the velocity and the path. Okay, so where this thing is denoted by IP, right? We know that this thing is exactly equal to. Now, there is a different methodology also available for steering guidance laws, and that is called as enclosure-based LOS steering. Enclosure-based line of sight steering. Notice that when we are looking at the look ahead distance, we are specifying everything in terms of this look ahead distance. That is our main parameter. But whereas when we are looking at an enclosure-based guidance scheme, you will see that we are actually specifying some circle of a certain radius. So we are specifying a circle of some radius r greater than 0, where the center of the circle is basically the craft's position. And we want to see that given a fact that we choose a good enough, large enough circle, it will intersect the point, the line connecting the two waypoints at 2 points. And this picture is a little out of scale, okay, because this point should have been the center, but then when I was drawing it out, my drawing is not so good that it turned out to be not the center, but off center. Okay, so imagine that that point is actually the center of the circle. Okay. All right. So in this case, the desired course angle. So in the previous case, we were getting our desired course angle in terms of the look ahead distance and the cross track error. Whereas here, what we'll be looking at is the desired course angle is given as tan inverse of y LOS minus y, x LOS minus x. So let's go back to this picture and see what is happening. So once I draw this circle, where is it intersecting? The circle is intersecting the line connecting the two waypoints. I'm picking that point, which is actually closer to the destination waypoint. And I'm then choosing that point's coordinates I need to compute. Once I know that fellow's coordinates and I know my current position, I simply take tan inverse of yn LOS minus yn xn LOS and minus xn. So basically, I'm trying to point my velocity vector along this radius direction. That's what I'm essentially saying. Okay. Now, notice here that when we want to look at this guidance scheme, we do not know yn LOS and xn LOS. We precisely do not know where the intersection will happen. So that needs to be computed as a part of the algorithm before we can come up with the desired course angle. Is everybody with me on this? Yes, making sense for everybody? Come on, please, you can respond yes or no at least.
Yes, sir.
How are we defining the circle, sir? Like the size of the circle?
The size of the circle is a parameter which we specify.
Okay. Yeah.
And we have to make sure that that is at least larger than the cross-track error. If that error, if the radius is less than the cross-track error, then the circle will not intersect.
Not intersect. Yeah.
Right. So we have to kind of make sure that that circle is a little cross-track error, and then therefore you're already seeing that there is a downside. There is a point where we may be in trouble, especially if we choose an R such that our R is less than the cross-track error, the magnitude of the cross-track error. This method will not work. We'll necessarily have to update our R value in order to get a proper line of sight guidance. Okay, so the idea here is that we know that x LOS minus xn square plus y LOS minus yn square is equal to r square because it lies on the circle. And we also know that tan of pi p is y I plus 1 minus yi divided by x I plus 1 minus xi. Okay, this is basically the slope between the two waypoints. Everybody with me so far? That same thing is also equal to the slope between the y LOS and the x LOS to the original waypoint, because they all are going to lie on the same line, right? This is the point, first waypoint, this is the second waypoint, and this is the point. All three of them lie on the straight line, so therefore slope between any 2 points should give me the same value. So this will basically give me the required equations to find out x LOS and y LOS. So I know everything else in this particular case. Once I specify a given R, I know what is the previous waypoint, I know what is the new waypoint, and I have two unknowns, which are this and this, and I can solve for them basically in order to get that. Once I get those 2 points, I can specify the desired course angle by simply taking the tan inverse of y LOS minus y and x LOS minus x. Okay. Notice that this is slightly different as compared to the look-ahead distance-based LOS scheme, where we were primarily worried about what is happening to the cross-track error when we were specifying our course angle in terms of the cross-track error and the look-ahead distance. Here we are specifying it in terms of some given radius r, where will the circle intersect the 2 points. And then based on that, we are trying to position our vehicle in that direction. You can already sense that since these equations, this at least the first equation is not linear, this computation is a little more involved rather than trying to look at what is, rather than what you're doing in terms of look ahead distance calculation. Okay, so this is a computationally little more intensive than the so the enclosure-based steering is more computationally intensive than the look-ahead-based steering. Okay, and the advantage is that the look-ahead-based steering was valid for all cross-track errors. We really didn't have to worry about whether this value of radius is larger than YPE or not. We didn't have to worry about that. We had our freedom to choose whatever YPE is. Based on that, we could come up with the guidance log. But here you have to be careful about that. So this always requires R to be greater than YP. Okay. And also here in this case too, you have your delta to be time varying. So you will notice that your delta is actually given by square root of R square minus YP square. So therefore you can actually know that your look ahead distance in an enclosure based scheme is actually naturally time varying. Whereas in a LOS based scheme, the proportional LOS based scheme, we could actually choose it to be a constant value if we wanted to. And then if we wanted to, we can even play around with it, and it gave us a little more degree of freedom to tune it. Whereas here it is by default time varying look ahead distance. Everybody with me so far? It is just introduced as another methodology for guidance. Okay, because when guidance methodologies were getting developed, many people proposed many different things. Now, not all things got clicked really well. Okay, some things did not have the advantage which other methods had, but they had to compare them in order to figure out which one is the best approach to go with. So eventually what has happened, most of the missile systems and other things, they started using look-ahead based LOS scheme rather than an enclosure-based LOS scheme, because it requires more computational power and it also doesn't always work depending on what value of R you choose. So because of these limitations, enclosure scheme is not as commonly seen, but some funny cases you may see it because it was used at least for some time in the past. But nowadays, mostly you will see it is always look-ahead based LOS guidance scheme that we'll use. Okay, so notice that when we were looking at the so-called desired course angle as pi p minus tan inverse of yp times, kp times ype, we were calling that as our look-ahead based LOS scheme. But sometimes what happens when you take such sort of a guidance scheme, which is only depending on the proportional part of the error, you may encounter that your desired trajectory is not actually matching well with what the exact line that you want to travel, especially when you have disturbances. So let us say that I wanted to travel from this point here to this point. Okay. And based on the cross-track error, so that is the YPE, I will be actually computing KP times YPE, plugging it here to get my desired course angle for my craft. That means I want to look at what is the velocity vector of my craft and how I should orient it with respect to the north. That is my chi desired. Okay, but suppose that there is a strong wind blowing from the right to the left. So let's say that there is a strong wind which is blowing in this way. Okay. Now what happens when YPE is 0, which means that the vehicle is actually on the path between the two waypoints, there will be no extra, the course angle will be directed towards straight towards the path, right? The desired course angle will simply approach pi p because this term will go to 0, right? But then because I have this wind which is acting on the vehicle, what will happen? It will try to push me off course. And I do not react until I actually see that I have veered off course. Only when I have a sufficient amount of a cross-track error accumulated, only then my controller will say, oh, wait a minute, you're heading in the wrong direction. Come on, let's try to correct our course. Okay? That is because we are only looking at a proportional error. We can avoid this idea by using a so-called integral error, where we can try to avoid these steady state errors even in the face of disturbances. Okay, when the disturbance is there, we still want to be able to be on our path. That is when we want to employ this so-called methodology of integral control. And the idea here is that we simply add an extra integral term where we are now taking an integral of 0 to t ype times delta t. Okay, so what is the average value of the cross-track error which will accumulate over the time? So when now a wind starts acting and it tries to keep me at a distance for throughout the time, I'll be able to compensate for that steady state errors using this integral action. This integral action will allow me to counter the disturbances which are coming in a steady state manner. Okay. More on this when you probably see in your assignments, where we'll try to compare between a P and a PI controller and see whether we are actually able to make this happen or not. Okay. Then we'll see that what is going on with how the integral action is actually helping us bring about this thing. And you actually saw some of it in your maneuvering and control course, where we looked at the linear systems. When we were looking at linear PID control, you looked at the idea that if I have an integral gain, I can make sure that my steady state error is precisely equal to 0. Right? The same applies even when I have a nonlinear system as well, which this is a nonlinear system because of the tan inverse over there. Okay. Still, I can show that with the integral action being there, I can actually try to compensate for this. But usually it is very tricky. Okay. This can be very, very hard to find an optimal gain and satisfactory stability margins. So if you want to make sure that it's not really finicky, right? We want to make sure that it works in most of the environments that we are interested in. And it's very hard to show, especially for a nonlinear controller, that what should be the integral gain that I need. To find that out is a big challenge. Typically, many people do it with trial and error, but again, when you do it with trial and error, you're not always sure that did I do the best? Was there any other value of integral gain that I could have chosen, which would have given me a better performance, is a question which always remains in your mind. Okay. So therefore, it's not a very great way to tune it. It gets the job done, but sometimes it can be a messy process to find out what the value of Ki should be, which will give you the desired behavior of the craft that you want. So in which cases people have kind of spent their time in order to figure out, can I find an alternative representation with guaranteed stability properties? And now here is where you see that all of our Lyapunov theory, which we were looking at, comes to our rescue, that we can actually make sure that given that a nonlinear system with a nonlinear control law, even though I do not know what the exact trajectory might look like, I can say something about stability. I can say that whether the system is globally asymptotically stable, that it will definitely achieve my path that I want to achieve. So those guarantees can now be achieved. So one such example is given here, where you will see that what I have done is I have taken this integral term of ype and replaced it by a variable called ypint. Okay, and what that ypint is not a simple integral of ype, but it is some complex function of ype. So I'm assuming that ype dot follows this dynamics. Okay. So based on this YPE, I'm going to substitute the value of yp int into here, and that will lead to my so-called desired cosangle error. And let us see why this sort of a function will be very helpful. Okay. Notice that what I'm doing here, I'm taking u times ype divided by square root of the look-ahead distance square plus ype plus some value k times yp int whole square. Okay. Where k is a value greater than 0 is a design parameter which I can play around with. Okay. That will determine how the dynamics of yp int changes over time. The advantage of choosing something like this is that if I now start looking at the cross-track error dynamics, ype dot, we saw that previously it was u times sine of I minus pi p, which in this case, okay, this sine of chi minus pi p will be the tan inverse of this plus this, right? Now, so let us see. Let's see if I can show this correctly. Yeah, so this chi minus pi p was tan inverse of kp times ype. So that's basically ype by delta. Ype by delta plus some k times yp int. That's what I have here, right? Is that making sense? I think I might have missed a delta there somewhere. Actually, this delta will be divided by the whole thing by delta. Is everybody following me on this? Let's take a look back. Let's make sure we understand this. Kp is 1 by delta, okay, and ki is given as some k times kp. So substituting these two into here, what do I get? Chi d will be equal to pi p minus tan inverse. So ype by delta plus k times by delta times yp int. Yes? Everybody with me so far? Okay. Now, therefore, when I want to compute this angle of pi p minus pi p, okay, so I'm basically looking at a triangle. This angle of chi d minus pi p is a triangle whose height is ype plus k times yp int, and then the base is delta. That is that angle. Everybody with me so far? So now I want to take a sine of that same angle, right? I want to take a sine of that angle. So what will it be? I have to compute the hypotenuse h, and that will be ype plus k times yp int divided by that hypotenuse. That will be the value of sine, correct? And that hypotenuse is nothing but square of this plus square of this square root of that. That's what I have here. Square of delta, square of this, square root of that. Everybody with me?
Yes, sir.
So that is how I'm getting this yp dot dynamics will be governed by this system. Now, if I assume that my u is greater than 0, which means I'm looking at some forward speed condition, I choose a candidate Lyapunov function, which is given by ype square by 2 plus k times yp int square by 2. Okay? And then when I take the derivative of it, first term will become ype times ype dot, and ype dot can be replaced with this fellow. Everybody with me so far? That's what I'm doing. And when I take the derivative, the first term, this thing is basically ype dot. Please tell me you are understanding or you are with me.
Yes, sir.
Okay. All right. Now, on the second one, we have k times yp int times yp int dot. Okay. Remember that this yp int, which we chose, has its dynamics governed by this equation which we had chosen for our results. Okay. So we'll now substitute that into here. So we'll replace this yp int by that value. Okay, and then you will see that a little bit of an algebraic manipulation, this is what will come out. Now, it's not really hard to see that this will come out, so I'm not going to bother doing the algebra here, but you can actually try that out on your own, and it's very easy to see that this is what should come out. Okay. Now, once this is what I comes out, and you see that actually I did do the whole process looks like. Yeah. Okay. int. So this is what should come out. Okay. And you can see that this thing will always be positive, numerator, the denominator will always be positive, and as long as u is positive, this entire value will be negative. Yes? No?
Yes, sir.
I'm just avoiding a little bit of an algebra. It's not really hard algebra. I just want you to appreciate the process rather than the actual math. We substitute everything into it, ype dot and yp int dot. The expressions for it, if we substitute it, we should expect to see this come out. So what happens is, as long as yp is not equal to 0 and yp int is not equal to 0, this value will always be less than 0. And that tells me that the equilibrium point ype and yp int equal to 0, 0 is globally asymptotically stable. Okay, this guarantee we were not able to get with our previous version of the integral LOS. We can't guarantee that. We can't show that for any chosen value of ki, it will always be positive. But here, no matter what value of k that you choose, which governs the dynamics of yp int, okay, no matter what value of k I'm choosing here, okay, the value of k that I'm choosing here, this system will always be stable, will always be globally asymptotically stable. So I don't have to deal with the process that, hey, I'm looking for these gains in a trial and error manner, and whether this system will be actually stable for all values or not. I need not be worried about it myself. Yes, I have introduced a more complex nonlinear system rather than a straightforward case where I was simply adding an integral term, but I have gained something in the sense that I have a guarantee that the system is globally asymptotically stable, which means that no matter what happens, the cross-track error will eventually come down to 0, and it will eventually always try to drive my system to make sure that my cross-track error gets down to 0. I hope you're able to understand the difference between the two. The idea there was that with this methodology, I had to choose the integral value of gain and then had to hope that it will work and it will be stable. But whereas with the newer methodology, I can actually prove stability of a globally asymptotically stable system. So I don't have to worry about my parameters. Now I can choose my parameters freely without having to worry about, oh, whether it will render my system unstable or not. Is that making sense? I know this might be a little bit to take in. As to why do I want to kind of suddenly avoid what I wanted to do before and try out a more nonlinear controller? The advantage I get is that I can guarantee stability. Let that sink in for a minute.
Sir,
Yes, Anand.
sir, could you go to the last equation that you wrote?
This one right here?
Yes, sir.
Hmm.
So why should yp int be 0, sir, for it to be negative? For this term to be negative?
No. So if yp, YPE. So as long as YPE is not equal to 0, no, the point is it is equal to 0. This value of V dot will be equal to 0 when YPE is 0.
No, sir, I'm talking about YP int.
YP int need not be 0 actually. Yeah, that's right.
Can be any value.
It's not required. Yeah, this is not required actually. This is not required. But again, we can apply the same methodology as before. You remember that we were looking at what are the points at which V dot will be equal to 0 and what is the invariant set of it. We'll find that the only invariant set for this will be when YP int is actually equal to 0. For any YP int not equal to 0, the system will not stay on that invariant set of
On
points.
the same point.
Yeah, so therefore it'll move away. So rendering the fact that there is only one equilibrium point, which is equal to YPE equal to 0 and YP int equal to 0. But you're right. YP int equal to 0 is not required here.
So this will be the only stable equilibrium.
That will be the only equilibrium point which you will have. Okay. Let me just make sure. That is an interesting point that you bring up, because YP int, it is non-zero, but YPE is 0, then too this is stable. Oh, that's a good point you have brought up, Anand. It is interesting. Actually, I have to take a look at this one more time. When YP int is exactly equal to, when YPE is 0, right? This derivative will be 0, which means whatever value of YP int I chose, it will continue to be there. So that is interesting. I have to actually take a look at it. Maybe they messed up somewhere. Okay, that's a good catch. So let me take a look at it one more time, and maybe in the next class we will try to revisit this problem. Okay, why the invariant set is not precisely this. Let me check here. YP int. YPE is 0. This thing will be 0. Yeah, I have to check. Okay, so therefore we will go through the algebra next time, just to make sure that we understand this correctly. Good catch. Okay, so there is a possibility that need not be YPE. YP int need not be 0. But in any case, you see, even if YP int is not 0, all that, let's say all those equilibrium points are still valid. In all of those equilibrium points, we still see that YPE will always go to 0. YPE can't be at a non-zero value. And then we can't expect V dot to be equal to 0. So since that is satisfied, it always ensures that YPE will definitely track down to 0. But yeah, you're right. It need not necessarily ensure that YP int needs to track down to 0. It can approach any value that it wants in some sense. But let me check upon that. Okay, Anand? I think you got a good point there. Either I have messed up in copying from the textbook, or there is something which has been remiss. So I'll take a look back at maybe the original paper. We may have to look back to make sure that this is working right.
Sir,
Okay. Yeah.
In our normal PI, this y int will be something like an accumulation of the error, right?
Yeah. So in our normal PI, this yp integral will simply be integral 0 to t y of tau. Sorry, not y. Ype of tau d tau. So it will be accumulation of the integral from 0 to t.
Here, like, we are not using the we are substituted that with some other equation itself. So,
yes, so it's
like,
not a technically perfect integral factor which you are getting out of it.
yeah, so like that could be one of the reasons why it's zeroness is not necessary. Like,
Yes, that's possibly right, because yp int need not be necessarily be equal to 0 once it starts tracking a particular point. Is that what you were asking?
yes, like if it had been accumulation of error, then we want it to be 0. But here with the expression itself is a different one.
Yeah. So the expression itself is different, but
Yeah.
no,
We
what?
sorry.
No, go ahead.
Like we need probably non-zero value of yp. Like if there is a presence of wind, like we need a value other than like not equal to
Correct. Yeah, I think that's right. That's what you're rightly pointing out. So we need a non-zero value of yp int, even though yp is 0, in order to make sure we are able to counteract the disturbances when the disturbance is present. That is what they're trying to tell me. But anyway, I do need to check upon it definitely once. So we'll revisit this topic tomorrow again. Okay. All right. So let me stop here. And in the next class, we will look at LOS guidance schemes where you are using heading autopilot. So far we were using course autopilots, which means we are trying to get a desired course angle. But next time we'll look at what happens when we want to look at a desired heading angle and deal with that. How do the line of sight guidance scheme changes? You'll see that it really doesn't change much. So it's more or less similar, but you're able to account for this disturbance effect. So whatever is that difference in crab angle, we'll include that into the disturbance term. So having this integral will help us make sure that our desired heading angle also tracks what it wants to track. But more on that tomorrow. Okay, so we have not covered it yet, so it won't make sense right now. Okay, sounds good. Any other questions? It's quite interesting actually. Let me see whether I got it right or whether I made a mistake in the copy. Yeah, let me check upon that. What is happening at yp int not equal to 0? What is governing the dynamics? Int not equal to 0. Yeah, you will have something which is coming into the course angle correction, which is trying to counteract your so-called disturbances. That is the idea. Yeah, so I think the math is not wrong. Maybe the understanding needs a little improvement. Yeah, we'll discuss this tomorrow. Okay, thank you guys. Let me stop recording now.